In 1929, it was discovered that the universe is expanding, and in 1957, we learned that we are made of chemical elements forged in the centers of stars. The sky isn't just pretty to look at, it's a window to the insanely powerful universe we live in. There's so much going on out there that we on Earth are usually totally oblivious to what's really happening. Why are we here? Why do we have stars and galaxies? It could have been something else entirely. Even though these things will eventually affect us, we tend not to pay attention until things get too serious, and that might have happened again. Throughout history, Betelgeuse has been one of the brightest stars in the sky, but now it's begun violently vibrating, and something terrifying is happening. Join us as we bring you all the details about what's going on with Betelgeuse and how it might just change our future along with its own. Betelgeuse isn't an ordinary star, it's never been. It's one of the biggest stars ever discovered, so massive that it even makes our Sun look small in comparison. With a mass roughly 20 times that of our Sun, Betelgeuse bears the undeniable mark of a supergiant star, and that's exactly what it is. Perception can be deceiving, though. From our vantage point, Betelgeuse might appear as just another distant star, but in reality, it holds a status far more profound. Located more than 640 light-years away from Earth, this distance might seem inconsequential at first glance, but in cosmic terms, it's monumental. If we had the capability to travel at the speed of light, a notion beyond our current reach, it would still take over 640 years to bridge the gap between us and Betelgeuse. But even under normal circumstances, we would need over 12 million years to make the connection, which is longer than the entire course of human civilization on Earth. That just puts into perspective how powerful this one star really is, and now it's been vibrating violently. We see stars as these objects in space that are on the calmer side, just existing regardless of their size, but this one proves that isn't true. The vibrations have scientists confused because Betelgeuse has never been still in the first place. It's always been known as a pulsating red supergiant, and it changes pretty much all the time. When the star expands, it looks brighter, and when it's contracting, it appears a little dimmer in the sky than what you usually might see. These fluctuations in luminosity take place over extended periods, ranging from tens to hundreds of days. What's even more interesting is that Betelgeuse showcases a wide range of brightness, spanning from approximately plus 0.5 to a more intense magnitude of 0, which is quite a massive difference when it comes to stars. These shifts in brightness actually happen in recurring patterns, with the shortest cycle lasting about 185 days and the longest extending to around 2,335 days. But sometimes, these fluctuations can also be more periodic and have more of a pattern that can be recorded. This phenomenon is called V-band magnitude. In February 2021, it registered one of its lowest V-band magnitudes in recent times, measuring at plus 1.614. While still relatively bright, this marked a departure from the customary radiance associated with Betelgeuse. Betelgeuse's significance isn't solely defined by its luminosity variations. Its distinct reddish hue stems from a cooler surface temperature of around 3,500 Kelvin, notably cooler than our Sun's 5,500 Kelvin. That might sound strange at first because, as we just mentioned above, the Sun is smaller than Betelgeuse, but it's still brighter on any given day. As it's cooler, it's going to be the polar opposite of our Sun. This cooler temperature also leads to a reduced energy emission per unit of surface area, resulting in its perceived dimness despite being one of the largest stars known to us. It's mostly been a relatively stable star, even though it's a pulsating giant. But what could the recent change from calm to storm be? Well, that's where things get more complicated. One of the most popular explanations here is that Betelgeuse's helium shell is burning. As Betelgeuse evolves through its stellar life cycle, it gradually exhausts the hydrogen in its core through nuclear fusion, converting it into helium. This is expected of a red supergiant like itself. What happens is that as hydrogen fusion slows down in the core, the star's outer layers expand, causing it to swell in size. This phase signifies the star's transition into the red giant phase. During this stage, helium accumulates in a shell surrounding the depleted hydrogen core. The intense heat and pressure in this helium-rich shell initiate a secondary nuclear fusion process known as helium shell burning. Helium nuclei begin to fuse together, forming heavier elements like carbon and oxygen. This process releases energy, counteracting the gravitational force trying to compress the star's outer layers. But the thing is, helium shell burning isn't as stable as hydrogen fusion in the core. It can actually lead to periodic energy buildups and releases, which makes things go down an unexpected path. These fluctuations in energy output can result in instabilities within the star's structure. The increased energy production causes the outer layers to expand, while the subsequent energy release causes them to contract. These expanding and contracting motions manifest as pulsations, causing Betelgeuse's brightness to vary over time. The intense energy generated during helium shell burning can lead to strong stellar winds, especially in red supergiants like Betelgeuse. These winds can carry away a significant amount of mass from the star's outer layers. The mass loss due to these stellar winds contributes to the redistribution of matter and energy within the star, further influencing its evolution. The outer layers pulsate outward during expansion and then inward during contraction, like rhythmic breaths. This rhythmic pulsation is like the heartbeat of the star, but when we see it as changes in its luminosity. While it's possible that this is what's going on, there are a few steps that have to be followed to confirm it. Astronomers employ a range of techniques to unravel the mysteries of pulsating stars such as Betelgeuse. Among these, photometry and spectroscopy stand out as key methods, each shedding light on a different side of things. Through photometry, astronomers meticulously monitor the star's luminosity changes over time. This involves capturing the amount of light emitted by the star at various intervals. As Betelgeuse pulsates, its brightness experiences fluctuations, revealing insights into the underlying processes causing these variations. This method provides a direct link to the star's dynamic behavior, allowing astronomers to track the details of its luminous output. Spectroscopy offers a more nuanced perspective, though, by analyzing the star's emitted light across a spectrum of wavelengths. This technique unveils valuable information about the star's temperature, composition, and motion. As Betelgeuse pulsates, its spectral lines shift and broaden, offering a glimpse into the physical conditions within its outer layers. These spectral changes can be studied to gain a deeper understanding of the mechanisms driving its pulsations. Bringing these techniques together enables astronomers to create a comprehensive narrative of a star's pulsation behavior. The information gleaned from photometry's luminosity measurements complements the insights extracted through spectroscopy and spectral analysis. This synergy allows astronomers to decipher the connection between the star's interior processes and the observed luminosity changes, painting a more holistic picture of Betelgeuse's pulsational rhythm. Yet to navigate the inner workings here, astrophysicists take an extra step. They harness the power of computational models to simulate the star's internal dynamics and behavior. These models encapsulate a range of factors, from equations governing stellar structure to the intricate dance of nuclear reactions and fluid dynamics within the star's core. They start replicating these processes virtually so they can observe how Betelgeuse evolves and its pulsations unfold under varying conditions. This process helps bridge the gap between theory and observation, making it that much easier to figure out what's really going on the surface of the pulsating star. But there's a lot more to it. Deep within the heart of stars like Betelgeuse, a remarkable process known as stellar convection can also be happening. This natural mechanism is responsible for transporting the energy generated in the star's core toward its surface, ensuring a delicate balance